It's a great pleasure and honor to be here today to celebrate with you the 50th anniversary of CERN. Poland has a very long association with CERN going back before it became a member. In a period it was difficult for Poland to become a member, and it was a very great moment in 1991 that I remember well when Poland became a member of CERN. And I'd like to take this opportunity to pay tribute to the very constructive role that Poland has played in the governance of CERN since that great moment 13 years ago. I'm not going to talk about CERN, but the things I'm going to talk about are based on my experience at CERN and have a great deal of relevance for CERN, many of them. The examples I'm going to give from science are mostly from CERN or from the physical sciences because I'm a physicist, but I'm quite sure that a biologist could find equally good examples and make the same arguments that I'm going to make about who benefits and who should pay for science. Over 200 years ago, at the beginning of 1782, the German philosopher and physicist Christoph Lichtenberg wrote in his diary to invent an infallible remedy against toothache, which would take it away in a moment, might be as valuable and more than to discover a new planet. But I do not know how to start the diary of this year with a more important topic than the news of the new planet. He was referring to the discovery of the planet Uranus, which was discovered in 1781. The question that Lichtenberg implicitly raised of the relative importance of finding answers to specific questions, what we call applied research, and of looking for fundamental knowledge, what we call basic research, is as relevant today as it was 200 years ago, perhaps more relevant. I'm going to argue that the search for fundamental knowledge, motivated by curiosity, is as important as the search for solutions to specific problems. The reason that we have millions of lasers in use today, reading barcodes in supermarket checkouts, in compact disc players, and in surgery, and hundreds of other uses, is not that somebody started a research program to look for tools to do those jobs. It's the result of research into the nature of the atom at the beginning of the last century. The discovery of lasers followed 40 years later, and even when lasers were discovered, those uses were not foreseen at the time. Similarly, electric light was not the result of a committee asking physicists to improve the performance of candles. I'm going to give many examples which show the practical and economic importance of fundamental research. But if fundamental research is valuable, why should it be supported from public rather than private funds? Why should it be paid for by governments rather than industry? The reason is that there are kinds of science which yield benefits which are very general and not specific to individual products, and hence the economic returns are usually not anticipated and they can't be captured and protected by an individual company. Most pure research is therefore funded by people or organizations, governments in particular, who have no commercial interest in the results. And the continuation of this kind of funding is absolutely essential, and this is something we have to explain to our governments. Once definite economic returns can be clearly seen, the private sector, industry, motivated by profit, is generally better placed to undertake the necessary research and development. Hence, much of applied research is and should be supported by industry. But it would be wrong to conclude from this, that argument I have often made, and sometimes people jump to the conclusion I'm saying government should only support basic research, industry only applied. That's not correct. Industry does some basic research, must do some basic research, although it's declining. Sometimes you can't see in advance which category the research will be in. If you carry out research into heart disease, for example, it might lead to a patentable drug. That will clearly be of interest to the biomedical companies. But if the conclusion is the need for more exercise or better diet, that's not of interest to the biomedical companies, and they might even not want to publish the results. So probably both sorts of funding are needed for this sort of work. Furthermore, governments have a very definite responsibility here to support not just basic research, but also applied research, mission-orientated research, research with a definite goal that is long-term or not commercial. For example, research related to the environment, to transport policy, or whatever, which is important and valuable for society, but does not lead to profit. And I'm going to discuss that in this talk. Now, I've got a long list of topics. I'm going to begin with basic science and end up with talking about energy research as an example of mission-orientated research into which governments need to put more money, in my opinion. This long program here is probably overambitious, and I expect I'm going to skip some topics, so I won't go through it now. I want to begin by discussing the difference between basic and applied research. Personally, I don't like these terms. After all, who can say in advance what can be applied? And I think a much better way is to define things is to base it on motivation. Let me begin with this remark, that I've found that in discussing science with non-scientists, often the problem is that people in industry and outside science use research in a different way than we scientists do. They use the word in a different way. And in industry, research often means innovation with existing technology. I'm not talking, when I say research, I'm meaning the research in the way that an academic scientist would mean it. This has sometimes led to a lot of misunderstanding with sociologists of science and so on. A second problem is that when you speak about the use of science, one sometimes gets accused of supporting the so-called linear model, in which basic research starts everything, drives applied research, and leads to industrial developments. Let me be very clear, I do not believe in that model. It sometimes happens, but it's not always like that. On the contrary, sometimes the flow is in the opposite direction. George Porter, who got the Nobel Prize for his work on flash photolysis, made the observation that thermodynamics owes more to the steam engine than the steam engine owes to science. And I believe that this is true. So the relationship between basic and applied science is certainly not linear. It's highly nonlinear. In fact, historical studies of modern research have repeatedly shown that the interplay between initially unrelated basic knowledge, technology, and products is so intense that far from being separate and distinct, they are all portions of a singly tightly woven fabric. Nevertheless, I think we can make a broad distinction between science, meaning knowledge, and technology, the means by which knowledge is applied, and between different forms of science, ranging from basic, which I would define as motivated by curiosity, to applied, or I prefer mission-orientated, designed to answer specific questions or address specific problems. Sometimes people define something called strategic research in the middle. Definitely, governments have a major role at this end of the spectrum, although industry also plays a role. Industry has a big role down here, but so do governments in many cases, as I shall explain. I would like to give just one example of curiosity, the idea of curiosity-motivated research, which was given by J.J. Thomson, who discovered the electron in 1897, in remarks he made to a committee during the First World War in 1916. By research in pure science, I mean research made without any idea of application to industrial matters, but solely with the view of extending our knowledge of the laws of nature. In other words, motivated by curiosity. I'll give one example of the utility of this kind of research that has been brought into great prominence by the war, First World War. I mean the use of X-rays in surgery. How was this method discovered? It was not the result of a research in applied science starting to find an improved method of locating bullet wounds. This might have led to improved probes, but we cannot imagine it leading to the discovery of X-rays. No, this method is due to an investigation in pure science made with the object of discovering the nature of electricity. Thomson went on to say that applied science leads to improvements in old methods, while pure science leads to new methods. And, I quote from Thomson, applied science leads to reforms, Pure science leads to revolutions, and revolutions, political or scientific, are powerful things if you are on the winning side. The important and difficult question for those funding science is how to be on the winning side. So I want to come now to some of the benefits of basic science. I would put first the contribution to our culture. Our lives are enriched, our outlook changed by knowledge of the heliocentric system, by the genetic code of how the sun works, why the sun is blue, the expansion of the universe, etc. I believe that scientists are too shy in making the cultural case for science. And this is a very old phenomenon, which goes back at least 2,500 years. This is a dialogue from Plato's Republic, in which Socrates and Glaucon are discussing the ideal curriculum for the university. And Socrates says, "Shall we set down astronomy among the subjects of study?" To which Glaucon replies, "I think so. To know something about the seasons, the months, and the years is of use for military purposes as well as for agriculture and navigation." And Socrates says, "It amuses me to see how afraid you are lest the people should accuse you of recommending useless studies." So it's an interesting example because astronomy is useful, but they're not prepared to make the cultural case. I think we should make the cultural case. I very much like the reply that Bob Wilson gave, the first director of the big accelerator lab, Fermi Lab, near Chicago. He was asked by a congressional committee, "What will your laboratory contribute to the defense of the United States?" And he replied, "Nothing, but it will make it worth defending." And I think it's a very good answer. And I think we should be a little bit more courageous about making the cultural case. When one makes the cultural case, you sometimes get the reply, in that case, the funding should be on the same level as public funding for opera. And I think that's misguided for two reasons. First of all, the opera performance is ephemeral. It's gone the next day, whereas science is cumulative. A better comparison would be with supporting the composers of opera. And personally, I would be very happy to see hundreds of millions of public money go to produce a new Mozart. But hundreds of millions are neither sufficient nor necessary to produce a new Mozart. In the case of particle physics, I think the globalization of the subject has made it much easier to make the cultural argument. I find to make the argument that the whole world is coming together at CERN, as they are, there are over 80 nationalities working at CERN to search for the nature of matter, is easy for people to accept. That this is something we shouldn't duplicate in the world, but that mankind collectively should carry out this mission is, I think, an easy argument to make. Next, it's not hard to convince oneself that expenditure on basic science often leads to discoveries of enormous economic and practical importance, and is highly profitable and is easily paid for itself. I'd like to give you a quote from Casimir, the famous theoretical physicist who became director of the Phillips Laboratory, and this quote comes from 1966. "I have heard statements that the role of academic research and innovation is slight, it's small. It is about the most blatant piece of nonsense it's been my fortune to stumble upon. Certainly, one might speculate idly whether transistors might have been discovered by people who had not been trained in and had not contributed to wave mechanics and the quantum theory of solids. It so happened that the inventors of transistors were versed in and contributed to the quantum theory of solids. One might ask whether basic circuits in computers might have been found by people who wanted to build computers. As it happens, they were discovered in the 30s by physicists dealing with the counting of particles because they were interested in nuclear physics. One might ask whether there would be nuclear power because people wanted new power sources, or whether the urges to have new power would have led to the discovery of the nucleus. Perhaps, only it didn't happen that way. One might have asked whether the electronic industry could exist without the previous discovery of electrons by people like Thomson and H.A. Lorentz. Again, it didn't happen that way. One might even ask whether induction coils in motor cars might have been made by enterprises that wanted to make motor transport, and whether they would have stumbled upon the laws of induction. But the laws of induction were found by Faraday many decades before that. or whether in an urge to provide better communication, one might have found electromagnetic waves. They weren't found that way. They were found by Hertz, who emphasized the beauty of physics and who based his work on the theoretical considerations of Maxwell. I think there is hardly an example of 20th century innovation what is not indebted in this way to basic scientific thought. These examples given by Casimir have a number of features in common. All of them were highly profitable. The uses were completely unforeseen when the underlying discoveries were made. There was an enormous time lag between the discoveries and their exploitation. The same was true for lasers, the first example I made. The basic work was Einstein's A and B coefficients in 1917. The laser wasn't discovered for 40 years after that. And finally, the people who made these discoveries did not themselves get rich. And I'm going to return to the consequences of these features later. So there are many examples of payoffs from fundamental research. And some people have tried to quantify them. In the 90s, the National Science Foundation made a study of the patents cited, the papers cited in patents. And they found that in industrial patents, 73% of the references were to public science, overwhelming basic research papers published by universities, 50%, 25% by government laboratories. A famous study by Mansfield in 1991 tried to estimate the rate of return on public investment in science, and he came up with the answer 28%. I don't think you can take that very seriously. It's a complicated, nonlinear business, but nevertheless, I think that the returns are very high. You might say, that's all very well, but returns from such esoteric subjects as particle physics are very, very unlikely. Well, maybe, but these researches, the ones I cited, were also regarded at the time as extremely esoteric, and I will give examples later of that, very unlikely to have benefits. Let's think about number theory. 30 years ago, if you'd asked people, what's the most useless branch of mathematics, they would probably have said number theory. But now it's in use in cryptology everywhere. In the case of particle physics, it's sometimes said that direct applications are inconceivable. But it's certainly not true. The counterexample is that I can conceive them. If there was a particle, a heavy electron like the muon, but a little bit longer lived, it would catalyze fusion. At one time, there were theories with magnetic monopoles, which would have catalyzed proton decay and given inexhaustible energy. So one can conceive of such things. Next, spin-offs and stimulations of industry. The devices and techniques used to carry out basic research often turn out to have other uses, and the demands of research stretch industry. And I'll give examples here from particle physics. As I've already said, direct applications are not the goal and are not expected, but they are not inconceivable. Here are some spin-offs. Accelerators themselves. There are about 15,000 accelerators in the world today, used for many things like sterilization of sewage, cancer therapy, source of synchrotron radiation and neutrons in biology, condensed matter physics. These are very different from the accelerators at CERN, but they all stem from the accelerators first built to do nuclear, then particle physics. And the developments at the frontier are driving these accelerators forward, a little bit like the way that improvements in Formula One racing cars show up later in ordinary cars. Particle detectors, crystal detectors, multi-wire proportional chambers, semiconductor detectors. Many, many developed in particle and nuclear physics, many, many uses in other fields that I've listed here. Informatics. Well, the most spectacular case is the World Wide Web invented at CERN, but there are many others which have moved out of particle physics into other domains. Superconductivity, the cables made to make high-field superconducting magnets, so-called Rutherford cable, were a result of particle physics. And there are many other examples in cryogenics, vacuum technology, electrical engineering, etc. A recent study of companies that had contracts from CERN showed that 38% of them had developed new products as a result, 41% said technology had benefited, 60% had strengthened their project management, and 52% said that they got marketing advantages. And the implications of this study, by the way, were that the closer the involvement between industry and CERN, the greater the benefit. So there are messages here that by working in partnership between CERN and industry, we can drive forward both sides. Both CERN can benefit from the industrial experience, and the industry can benefit in turn. Some people think that giving a long list of spin-offs is enough to justify particle physics. I don't believe that's the case myself. To do that, you would have to make an analysis of the value of the benefits, and you'd also have to ask, what would have happened if you'd spent the money at CERN on something else? It's not surprising if you spend a large amount of money on high technology that things spun off. It would be surprising if they didn't. Nevertheless, these spin-offs are important, and they should be set against the value of the public investment. But I don't believe that they are in themselves the justification for that investment. The last benefit of basic science is that it provides excellent training in problem solving for people who go into applied research or industry, many of them afterwards. And this also creates valuable networks between these people, especially when they work together at CERN. Many of the students who work at CERN later go into industry, and they retain networks of connections with physicists working across the world who began their lives at CERN. And finally, these exciting frontier sciences have a flagship role in attracting children to science and technology. Funding of basic science is important for society as a whole, for cultural reasons, but it's also tremendously, on average, economically beneficial. But it is not in the interest of any individual investor to support it. Those who make fundamental discoveries generally do not reap the benefits. That the laws of nature cannot be protected, the applications are too long-term and unpredictable, and the cultural and educational benefits, of course, do not generate direct profits. The heirs of Newton, his children and descendants, if he'd had any, he didn't, would be rich if Newton had been able to make a patent on calculus, but you cannot protect the laws of nature. Very few scientists have the foresight of Faraday, who was asked by the British Prime Minister, Gladstone, what use is electricity? And it's said that he replied, "One day, sir, you will put a tax on it." But that's very untypical. Much more typical is Rutherford, who discovered the nucleus, who in the 1930s said, anyone who expects a source of power from the transformation of atoms is talking moonshine. That's the person who discovered the nucleus, could not foresee the benefits. Although quantum mechanics underwrites modern electronics and lasers, even with the benefit of hindsight, investment in research on quantum mechanics would not have been a good commercial investment. The time lag was too long, and it would have been impossible to protect the results and prevent others also using them. So investment in basic science is not of interest for any individual company, but it is important for society as a whole. And this means it's what economists call a public good, which must, like lighthouses and defense, be supported by government. Once it's there, it's rather difficult to prevent everybody else using it. So, government should support basic science on the benefits of the directly acquired knowledge, the spin-offs, and the training. And when profit can be foreseen, we can rely on industry to do the job. But this leads to two questions. If funding is not in the interest of any individual company because they can get the results later, is it in the interest of any individual country? Can't we leave it to the Americans to do it and take their results? And then, how should governments choose what science to fund and at what level? I think that developed countries have, first of all, a responsibility to contribute in the interests of society as a whole. But in any case, an active basic research base is necessary to sustain and foster technological development. In fact, you cannot just take science off the shelf and use it. In that sense, maybe it's not quite a public good. Skills and tacit knowledge, the skills how to use things, are needed to adopt, adapt, and use technology. You need to be in the field to be able to quickly exploit discoveries made by others. So I think that if we just said we'd leave it to the Americans, we'd be left to be a technological colony of the Americas forever. We need our own tech, even if we're going to use their results, we need our own science. First of all, we should be contributing, but secondly, we need our own science to be able to adapt and use technology developed elsewhere. I can't object if people try to use economic arguments in deciding how to partition funding between different bits of science. However, it's been rightly said that both forecasting and innovation are highly stochastic processes. So the probability of correctly forecasting an innovation being the product of two low probabilities is, in theory, close to zero. If Rutherford, who discovered the nucleus, could not foresee nuclear power as late as 1935, that quotation, if Rutherford could not foresee nuclear power, do we think that a government committee could do better? I think not. Earlier, I suggested that Faraday might have foreseen the application of electricity when he told Gladstone that one day it would be taxed. However, in 1867, 9 years after Faraday's death, a meeting of British scientists made the following announcement, and I will quote, "Although we cannot say what remains to be invented, we can say there seems to be no reason to believe that electricity will be used as a practical mode of power." It was in 1867. Similarly, there's a well-known quote from Thomas Watson, the founder of IBM. In 1947, Watson said, "A single computer could solve all the important scientific problems of the world involving scientific calculations. He did not foresee any other uses for computers." So it's very, very difficult to foresee the uses of these things. This unpredictability, I've argued, is one of the reasons why its government in the first place has to support fundamental science. But it also means that in practice it's probably impossible and very possibly dangerous to distribute funding for basic science on the basis of guesses about what's going to be useful. That would throw out many of the good things. And I actually think that the traditional criteria on basing the choice on the excellence of the science and the people is the correct one, probably, in science. After all, money is more abundant than brains. The fact that basic research is unpredictable does not mean that economic incentives to solve specific problems, mission-orientated research, is futile. On the contrary, let me give some examples. Mission-orientated research, you can just go in with money and do it when the conditions are correct. In the 19th century, scientists looked for methods of artificial fixation of nitrogen, but they didn't succeed until in the First World War, Germany was deprived of fertilizers, and there was a great need to fix nitrogen, and a solution was quickly found. Likewise, US science and technology and money met the political imperative to put a man on the moon by 1970. But it's important to understand when such incentives are likely to work and when they are not. President Nixon announced a war on cancer, which he modeled very explicitly on Kennedy's announcement that America would put a man on the moon. He said, "We will do the same thing and cure cancer." And it failed. And the reason is clear. The principles of putting a man on the moon, the physics, was well understood before the space program began. But our knowledge of the biological principles underlying the growth and mutation of cells is still limited. If and when general cures for cancer are discovered, it's likely they'll be the result of fundamental advantages in biology, and they're going to be highly profitable. But pharmaceutical companies don't put money in this research for that reason, because if they did discover these principles, it's very unlikely that they could keep them for themselves. And that brings me to applied research. it's a general principle that when we're close to the market, government should keep out. Industry can get on with it. And industry generally wants to innovate with current technologies that can be priced and predicted accurately, and we can trust them to get on with it. But governments do have a major role in public goods that are not commercial as well as long-term, such as research related to the environment, traffic control, etc. I'm going to come back to that in a moment. Unfortunately, governments do not pay attention to this advice, and they still try to guess what's going to be useful and base science funding on that.